The map showed solid ground where thousands of invisible earthquakes were already firing. For decades, instruments designed to track the shifting American West recorded absolutely nothing out of the ordinary in this incredibly quiet zone. Silence usually implies safety. Here, that complete absence of a traditional signal was the very first indication of a massive, deeply buried fracture. Researchers from the USGS, UC Davis, and the University of Colorado Boulder recently aligned decades of seismic data to reveal an ancient fault system sitting directly under Northern California. This hidden structure does not break the surface, leaves zero geological scars, and lacks any visible topographic warning. It operates entirely in the dark. Instead of large, obvious ruptures, the boundary continuously produces low-frequency micro-earthquakes sitting near magnitude 0. Most residents expect tectonic danger to physically rattle windows and aggressively wake neighborhoods. These tiny underground events barely register on highly sensitive equipment. A single tremor measuring 0 releases almost zero measurable energy, making it remarkably easy for analysts to dismiss as random background noise. Hundreds of them repeating from the exact same subterranean coordinates suddenly outline a vast geological machine. That dense repetition allowed advanced algorithms to seamlessly stack the faint signals together like layered echoes, finally illuminating a horizontal plane of broken rock. Before this technological alignment, the prevailing models firmly assumed subducted plates in this specific region sank downward at steep, easily tracked angles. The actual rock fragment ignored those academic models completely. It stayed remarkably shallow, sliding sideways through the crust without ever exposing its edges to the sunlight. Finding a new fault immediately rewrites local hazard assessments, but this specific discovery forces a much larger structural correction. The Mendocino Triple Junction famously marks the chaotic intersection of the Pacific, North American, and Gorda plates, creating an exceptionally complex geological knot. Simple tectonic intersections feature clean, highly predictable lines. This junction features deeply overlapping fragments, including a remnant of the Farallon Plate known as the Pioneer Fragment. The immense Pacific Plate constantly drags this ancient block horizontally beneath North America. Earlier geological surveys entirely missed this interaction because they exclusively looked for vertical subduction angles and sharp surface-level offsets. When the ground appears pristine from the sky, traditional field mapping severely struggles to identify the chaos occurring miles below. Stacking those microscopic tremors permanently solved the subsurface imaging problem. By combining signals thousands of times weaker than typical earthquakes, scientists effectively traced the Pioneer fragment's previously hidden edges. The picture that ultimately emerged does not feature 3 neat tectonic pieces interacting cleanly. The new data exposes a crowded 5-plate configuration heavily layered deep inside the crust. More structural edges mathematically mean more active boundaries, drastically increasing the potential pathways for crustal stress to travel. If extreme pressure builds along one concealed surface, it can readily transfer to another, redistributing the massive mechanical load across the entire region in highly unpredictable patterns. A creeping fault section slowly releases strain while a neighboring locked section aggressively absorbs it. Deep fluids migrating through the rock further weaken the active zone, physically lubricating the boundary and driving the constant swarm of microquakes. That constant internal adjustment shows the system is highly active right now, continuously reshaping the coastal stress field. Every small subterranean slip redistributes the regional burden. You might naturally assume that releasing energy gradually makes a fault significantly safer. This slow motion actually complicates the long-term risk profile. strictly because parts of the flat boundary slide quietly, while other adjacent sections remain firmly stuck. Those silent, locked gaps do not release tension. They continuously accumulate it. Tracking the tiny tremors helps seismologists actively map exactly where the rock yields and where it dangerously resists. That resistance builds toward much larger kinetic releases, directly mirroring the events of the 1992 Cape Mendocino earthquake. Measuring magnitude 7.2, that specific rupture struck the coast with extreme force, but its exceptionally shallow origin completely baffled scientists at the time. The ground movement did not fit cleanly into the existing tectonic framework, leaving researchers with a major anomaly and no clear structural cause. The newly mapped Pioneer fragment finally provides the missing physical context, perfectly aligning the 1992 epicenter with the buried horizontal boundary, linking a historical magnitude 7.2 release to a hidden structure that eluded detection for decades alters the entire baseline understanding of coastal vulnerability. Residents instinctively trust official hazard maps to clearly show them exactly where the Earth might split. When the surface topography lies, that deep trust becomes a significant community liability. A hidden fault can sit directly beneath heavily populated areas, entirely omitting the visible fault scarps that typically warn developers to avoid building overhead. The coastal land appears perfectly ordinary while thousands of microquakes continuously fire just out of reach. Finding this particular boundary required immense scientific patience and a massive array of highly sensitive monitors precisely tuned to the rock's lowest frequencies. The effort ultimately uncovered a geological mechanism that operates entirely below the threshold of human perception. This specific region shakes constantly, yet residents feel absolutely nothing. Relying strictly on physical sensation creates a deeply false sense of security in coastal areas dominated by low-frequency earthquakes. Tectonic tremors represent massive plate-scale loading, directly tying these incredibly faint signals to the extreme forces driving the Pacific Plate northward. The vast energy source driving these events easily dwarfs human-made disturbances like localized geothermal drilling. What physically feels like absolute stillness is actually a gigantic geological machine continuously grinding, sliding, and aggressively adjusting its internal geometry. If a single undetected structure can significantly alter the hazard models for Northern California, the broader implications stretch far beyond one isolated coastline. Dense sensor networks and advanced signal stacking algorithms can deeply scan other complex junctions across the globe. Applying these modern analytical techniques to different subduction zones will inevitably expose additional hidden tectonic features. A hazard map that looks perfectly finished today is merely a rough draft waiting for a higher resolution instrument to correct it. Older geological surveys missed the Mendocino structure primarily because they relied on sparse sensor networks that gathered far too few data points. Without sufficient instrumental density, the background chatter of the Earth remains completely indecipherable. Once sensor placement dramatically increased, the random noise finally organized into a highly coherent shape. The deep ground did not abruptly change its behavior to become visible. The scanning technology finally evolved enough to catch the continuous whisper of ancient rock. Every established hazard model for this coastline just became functionally obsolete. Subduction zones were traditionally drawn with steep downward trajectories where oceanic plates plunge cleanly into the Earth's mantle. The Pioneer fragment ignores that assumed geometry entirely, remaining remarkably shallow and creating a broad, flat contact area that fundamentally shifts how seismic energy propagates. A horizontal fault plane allows extreme tectonic motion to spread across a vastly wider subsurface footprint. That flattened architecture significantly complicates emergency planning, completely removing the comfort of a single, well-defined rupture line. You are no longer dealing with a distant threat located miles to the east or west. The active boundary actively rests immediately beneath the ground you stand on. This overlapping subterranean structure connects directly to the massive Cascadia subduction zone extending far up the coast. Cascadia possesses a highly documented history of severe impacts, famously rupturing in the year 1700 and generating a massive tsunami that traversed the entire Pacific Ocean to reach Japan. The Mendocino Triple Junction sits exactly where this huge offshore system heavily intersects with the San Andreas Fault. Intersecting tectonic forces create immense mechanical crowding, forcing crustal fragments to shear and physically fracture in highly unconventional patterns. Unconventional geological behavior inherently resists standard monitoring techniques. A fault section that creeps slowly, heavily lubricated by migrating deep fluids, completely bypasses the brittle snapping mechanism responsible for generating traditional high-frequency seismic waves. It steadily releases strain in microscopic increments, actively drawing a slow-motion map of its own hidden contours. These thousands of microscopic data points seamlessly merge into a highly detailed diagnostic image of the deep crust. When tremors cluster tightly in a very specific sector, seismologists immediately identify discrete zones of concentrated stress. When those clusters migrate over time, the shifting pattern perfectly illustrates transferring pressure within the solid bedrock. The rock consistently tells its own story through continuous low-level vibration. Understanding that story thoroughly requires acknowledging that geological danger rarely announces itself with obvious surface scars. Most casual observers logically expect an active tectonic boundary to aggressively split hillsides or dramatically warp concrete roadways. The Mendocino anomaly left the coastal landscape completely unblemished. High-resolution aerial photography revealed absolutely nothing. Field surveys actively walking the terrain documented perfectly normal topography. Traditional geological mapping found no clean, visible line to follow, leaving the safety charts completely blank. The surface essentially acted as a massive cover, completely concealing the exceptionally complex five-plate interaction churning far below. The old maps failed entirely because they fundamentally assumed the visible landscape accurately reflected the subterranean reality. When the theoretical model and the hard data clash, the ground always wins. Redrawing the coastal boundary means accepting that extreme stress actively flows through deep networks nobody previously considered. Every new connection substantially increases the number of potential pathways a future rupture might aggressively follow. This realization deeply unsettles the global scientific community. A hidden fault is incredibly difficult to accurately map, and an unmapped fault is exceptionally easy to fatally underestimate. Underestimation constantly constitutes a critical error in established earthquake country. The Earth routinely utilizes forgotten tectonic hardware long after older models officially discard it. The massive Farallon plate began subducting millions of years ago, yet its heavily fragmented remains still exert immense influence over modern seismic activity. Time does not magically erase these deep geological structures. It solidly buries them beneath heavily accumulated sediment and deeply flawed assumption. Uncovering them strictly requires immense computational power and a stark willingness to question established maps. Finding the Pioneer fragment took several decades of observation and the precise digital alignment of countless microscopic events. If this heavily monitored section of the American West can successfully conceal a major plate boundary for that long, the implications for less studied regions are genuinely staggering. Exceptionally complex tectonics visibly exist worldwide. Countless coastal cities sit directly above deep sedimentary basins that effectively mask underlying bedrock fractures from standard observation. The advanced techniques pioneered in Northern California offer a radically new lens for evaluating these environments. Listening to the remarkably persistent whisper of low-frequency events provides a highly active scan of the deep crust. It clearly highlights exactly where the massive friction yields and where the rock firmly holds. This continuous feed of seismic data heavily shifts the scientific focus from historical prediction to real-time observation. Instead of simply guessing when a fault might break, researchers now actively watch the massive system actively load and incrementally adjust. News cameras only point at the ground after it forcefully breaks. Media coverage heavily prioritizes sudden, massive releases of kinetic energy. The exceptionally slow grinding reality of tectonic adjustment happens quietly in the dark between the sensational headlines. Thousands of magnitude 0 tremors continuously fire without ever waking a single dog or rattling a solitary window pane. Yet these totally imperceptible movements strongly carry the exact same scientific weight as a major surface rupture. They actively trace the precise subterranean geometry of the regional risk. Without highly accurate geometry, emergency planners and structural engineers operate essentially blind. The calculated distance from an active fault line strictly dictates local building codes, insurance rates, and emergency evacuation routes. Moving a plate boundary on a hazard map physically alters the documented exposure level for millions of coastal residents. The Mendocino discovery definitively shows that some of the most critical structural information will never appear to the naked eye. It arrives permanently hidden within data patterns of extreme statistical subtlety. As sensor array density rapidly improves globally, the detected volume of these highly subtle patterns will inevitably increase. More recorded data dots will strongly form more definitive fault lines. New constellations of underground stress will rapidly emerge from what was previously considered mere background noise. The Earth continuously broadcasts its deep mechanical status to absolutely anyone possessing the right sensitive instruments, ignoring those faint acoustic signals simply because they currently fail to cause immediate structural damage guarantees future catastrophic surprise. The deep ground beneath Northern California did not recently become more highly fractured. Our technological capacity to comprehend that massive fracturing merely caught up to the hidden geological reality. Every new dataset heavily refines the subsurface picture slightly more. Geologists once viewed the Mendocino Triple Junction as an exceptionally complex but fully understood meeting point of three major plates. The advanced LFE signal stacking completely shattered that overly simple concept. A massive 5-piece configuration dramatically multiplies the sheer number of active boundaries actively interacting at depth. Hidden geological faults rarely operate in pure isolation. They firmly connect, physically overlap, and constantly transfer immense mechanical load across the entire tectonic network. This deeply interconnected architecture heavily suggests that future extreme ruptures might traverse pathways that currently remain totally unmapped. If a major earthquake aggressively follows an unexpected deep route, the resulting extreme surface shaking can rapidly concentrate in areas deemed relatively safe by outdated scientific models. Correcting the official hazard assessment strictly requires immense patience. The Earth absolutely dictates the measured pace of scientific discovery. Advanced seismometers can only accurately record the specific signals the crust ultimately decides to generate, while the creeping sections of the ancient Pioneer fragment readily broadcast their precise position through continuous microquakes. The heavily locked portions remain entirely silent. Absolute silence in a massive fault zone does not remotely indicate a lack of a severe strain. It fiercely highlights the exact deep locations where tectonic pressure is currently maximizing. The continuously whispering rock brilliantly illuminated an ancient, completely horizontal fracture safely hidden for millions of years. Those incredibly faint signals effectively redrew the fundamental structural map of the American West. And that massive shift leaves one critical issue completely unresolved as the seismic data relentlessly continues to stream into the labs. If the only reason this extremely massive boundary was successfully found is because it finally produced enough tiny signals to digitally trace its shape, exactly how many other major tectonic structures are currently locked tight, continuously building extreme pressure in absolute silence directly beneath us,